turn now to the topic of area, finite sums, and sigma notation. This brings us to chapter 5 in the Thomas textbook, and for those of you following along in the Thomas textbook, this corresponds to section 5.1. So one of the things that happens at this point in the course is that we kind of shift gears. Up to this point, we've been talking about the same, basically the same two concepts, limits and derivatives. We first encountered the limit, then toward the end of limits we came up with this very special definition of a particular limit that we called the derivative, found ways of finding the derivative without having to calculate a limit directly, and then did applications of the derivative. But basically it's been these sort of two concepts, and what we're doing now is going to feel very much like shifting gears. We're going to be talking about area, and in a couple of sections you're going to see that there's a very close connection between area and derivatives. But for now, we're just going to be talking about area. So let's imagine that what you want to do is you want to find the area under a curve. And when I say the area under a curve, what I mean is if I draw this line here, let's suppose that what I want to do is I want to find the area that lies between. I'm trying to think of how to draw this the best. I want to find the area that lies between the curve y equals x squared plus 1, the x-axis, the y-axis, and the line x equals 1. So there are these two vertical lines on the left and right, and then there's the x-axis on the bottom and a curve on the top. So one thing you could do if you were willing to settle for just an approximation of the area is you could try to come up with some rectangles that sort of fit within within the region you're trying to measure. I'm going to do this with 4 just to show you what this looks like. So let's suppose that I divide this interval 0, 1 into 1/2, and then I divide it again so that I have these 3 points in the middle of the interval. So I've divided the interval 0, 1 into fourths. And let's just clarify. We want to find the area, the approximate area under y equals x squared plus 1 on the interval 0, 1. That's what we're doing. So one thing that I could do is I could say, let's pick the point that has the maximum value, the point along the curve y equals x squared plus 1 that has the maximum value in each of these subintervals. What we're calling it for subinterval is, we'd say, for example, that 0 to 1/4 is a subinterval of 0, 1, and then so is 1/4 to 1/2, so is 1/2 to 3/4, so is 3/4 to 1. So what we want to do is pick the maximum value of the function in each of the subintervals. Because this is an increasing function, we see that it always gets larger and larger and larger as we move to the right, so it's fairly easy to pick the maximum value. I can pick that value right over 1/4. That's going to be the highest value in the subinterval 0 to 1/4, and similarly that will be the largest value in the interval 1/4 to 1/2, and I keep going and I get those 4 red dots that give me the largest value. So let's now draw a rectangle. Let's actually draw 4 rectangles where each rectangle has as its width the length of the subinterval, and its height is the red dot that gives the highest value in each subinterval. So I've got that rectangle, that rectangle, that rectangle, and that rectangle, like that. And what I can do is let's just shade these in so it'll be clear what rectangles we're talking about. That one, there's that rectangle, that rectangle, and that rectangle. So it would certainly be a reasonable statement to say that the approximate area under the curve is equal to the sum of the areas of these 4 rectangles. Obviously there are some problems with that estimate because we can see that each rectangle sticks out a little bit above the curve, but it's not a completely unreasonable way to estimate the area. So let's just see what we would get if we did that. So if we plug in, actually let's just write out the 4 areas. Let's say, let me actually write them here. There's green, there's pink, Okay, so there's the four rectangle. I've color coded the lines that I'm going to add up, and each one is going to have the area of a rectangle on it. So what we can see is that each rectangle has a width of 1/4, because that's really what we did. We took an interval of length 1 and divided it into fourths, and its height is just going to be when we plug in one of these endpoints of the subintervals into x squared plus 1. So the yellow rectangle is going to have an area of 1/4. Actually, let me do it in that order. 1/4, 1/16 plus 1. Where did I get the 1/16 from? I plugged in 1/4 and I squared it. So this is what I have here is this is the width and this is the height, because this point here is 1/4 comma 1/16 plus 1. Okay, so that's the first rectangle. Let's do the remaining ones. So we have 1/4, and this is going to be 1/2 squared gives us 1/4 plus 1. Here we have 1/4, and this is going to be 3/4 squared is 9/16 plus 1. And then I have 1/4, and for the green rectangle, the point we're using is 1. We square that and we get 1 plus 1. So this is going to be 1/4, 17/16, 1/4, 5/4, 1/4, 25/4, and 1/4, 2. So I now have a list of all the areas of each of these rectangles, and I can simply add them up. So what I can say is that the area under the curve is approximately, it's not exactly equal to, but it's approximately equal to just the sum of all of these terms. We can see is that they all begin with 1/4. So when I add up all four of these terms, I can simply pull out a factor of 1/4 and add in 17/16, 5/4, 25/4, and 2. And if you add all that up, that actually comes out to 94 over 64, or 47 over 32. So that's the approximate area. This is the approximate area under the curve y equals x squared plus 1 on the interval 0, 1. It's not the exact area, but it's an approximate area. Now, note that what we did was we chose the particular points to plug in because they were the largest value in each subinterval. In other words, there's no point in the subinterval 0 to 1/4. There's no point other than 1/4 that's going to give me a higher y value when I plug it in. Just the same for the blue rectangle, the subinterval 1/4 to 1/2. 1/2 is the number that I can plug in that's going to give me the highest y value in that interval. So this is not the only way to choose a point. Another way that we can do it is like this. We can choose the lowest point. So here, if we were asked simply to find an approximate area under the curve, oops, this should have been x squared plus 1, area under the curve y equals x squared plus 1, and instead we decided to choose the lowest value in each subinterval, what we would do is we would choose this point, this point, this point, and this point. So I'm just going to zip through writing out what these areas are. Okay, so we can see that if I choose the lowest possible y value in each subinterval, then I get a different approximation. This approximation is 31 over 32. So we've seen now two different approximations. Would it surprise you to learn that the actual area under this curve on the interval 0 to 1 is 4/3? Now, 4/3 is approximately equal to 1.333. I've written out what these decimal approximations are. This is approximately equal to 0.96, and this is approximately equal to 469. So 1.33 is actually somewhere between these two estimates. That shouldn't surprise you because you can see this set of rectangles seems to include a little too much area, so it's going to be bigger than the true value. This set of rectangles includes too little area, so it's going to be smaller than the true value. This number, which we haven't yet learned how to calculate, falls between them because it doesn't include too much or too little of anything. It's the exact right answer. So the point is that what I've done is I've shown two different ways that I can choose rectangles that will approximate the area under the curve. By the way, you might ask, how come I chose 4 rectangles? It's just a convenient number. In any given problem, we would tell you how many different rectangles to divide the subinterval into, but it's sort of typical to demonstrate it for the first time with 4 rectangles. So that's all right. So this is what we're doing for this section. Is we're talking about getting approximate areas under the curve as well as some applications of area under the curve by using rectangles. So I want to go through the different ways that you can choose the height of the rectangle in each subinterval. What we saw in the previous example was that we chose the highest and lowest point in one example we chose the highest point in the subinterval. In another example we chose the lowest point in the subinterval. Because the function was increasing, those happen to correspond to the right and left endpoints of the interval respectively. But there are actually a few different paradigms that you can use to choose the representative point in each subinterval. So the first one, I've put up the ones that we used, but with a little bit more of a complicated drawing. And by the way, I'm not specifying what the function is that's shown in purple, but we are interested in finding its area on the interval 0, 1, and I'm saying that we're doing this with n equals 2. So when I write n equals 2, what that means is that I'm choosing 2 rectangles or 2 subintervals. So what I've done really is to divide the interval 0 to 1 into halves. So the first paradigm is we can choose the highest value in each subinterval, and that's what these red dots are showing. As you can see, it just so happens that the highest endpoint in the first subinterval is right at x equals 0, and the highest endpoint in the second subinterval is the second red dot here that appears sort of at a peak in the middle of the second subinterval. It's not at the right or left endpoint. So let me just show you what rectangles you get when you do that. This, by the way, is called the upper sum. In other words, when I choose the rectangles, when I choose the rectangles to correspond to the highest point in each subinterval, this is called an upper sum. Okay, so the next paradigm is, also just notice that sometimes these rectangles really don't match the curve very well. That's okay. That's something we can always take care of just by drawing more rectangles. I realize the way I've drawn this intentionally, it's a little bit hard to see why this green rectangle is approximating anything about that curve. And it's simply because we created a rule and said choose the highest value in that subinterval and draw a rectangle whose height is given by that highest value. So let's go to the next example, the lowest value in each subinterval. Here, the lowest value is this red dot, and it appears in the middle of the first subinterval, and the lowest value in the next subinterval is actually the left endpoint of that subinterval. I'll just shade these in. And as you can see, these rectangles don't really match the curve very well either, but that's okay. We're just following that particular paradigm. This has the name lower sum when we choose the lowest value in each subinterval. And as you can see, the upper sum is always going to be greater than or equal to the lower sum. The only reason I have to put in equality is it's possible that the lowest and highest value, that the function could be a constant, in which case the lowest and highest value in each subinterval would be the same. Normally you're going to get something like this, where for the upper sum we have enormous rectangles and for the lower sum we have tiny rectangles. Okay. The next paradigm that we can use is we can choose the right endpoint of each subinterval or the left endpoint of each subinterval. In the first example that we did in this for this section, it probably looked like that's what we were doing, but actually it just so happened that the left and right endpoints were also the lowest and highest values in the interval. What I've drawn here is an example where that's not true. So we can do is we can draw in this rectangle given by the height of the right endpoint of the first subinterval and then this one given by the height of the endpoint of the second subinterval. Now for the here on the right, paradoxically, even though I've switched right and left, we're going to do the left endpoints. So here I'm choosing the height of the left endpoint of the subinterval of each subinterval like that, and I'll just shade these in. Okay, and these don't really have special names. These are just the right endpoint and left endpoint methods. Another method that you can use is you can choose the midpoint of the subinterval. We use that one a little bit less. It comes up in a different context, but I thought I'd put it here just for completeness. Draw in these rectangles here, and I'll shade them in. Okay, so we now have a couple of different ways of choosing five of them to be exact, five different ways of choosing the the height of the rectangle that's going to represent each subinterval. Our textbook makes a fairly large issue of the upper sum and the lower sum. In other words, the first two methods that you see here. Other textbooks that I've used focus on the right endpoint, left endpoint paradigm. Fortunately, a lot of the functions that we're going to be working with, let me just go back for a minute, look like this. So as you can see, here, what I did was I indicated when I was doing this example in the previous part of the video that we were choosing the lowest value in each subinterval. That's true. That's why we chose the left endpoint. But notice that if the function is increasing on the entire interval, then that means that its lowest value is always going to be as far to the left as possible. As you can see from the later examples that I did, that's not always going to be the case. So upper and lower sum really are different methods of choosing the point from right and left endpoint. We're going to do some examples with all of them in this section, but just be aware that they often are going to lead rather the upper sum and the lower sum are often going to lead to right or left endpoints of the subinterval, just because we're going to choose functions that are monotone on an interval in many cases.